Have you ever just spun a coin on a table, watched it blur into that perfect little sphere, and then listened as it started to wobble, rattle, and shake right before it finally came to a rest? I mean, why does it actually do that? It's such a simple, everyday occurrence, right? Yet, hidden inside that tiny wobbling piece of metal is a whole world of complex physics. And honestly, that's exactly the kind of natural, everyday curiosity we're going to unpack today. So, welcome to this explainer. Today, we're diving deep into a really fascinating educational journey straight out of Chapter 7 of the curriculum. It's appropriately titled, How Things Work. I'm absolutely thrilled to guide you through this because what we're really looking at here is that seamless, beautiful transition from pure, joyful childhood play straight into the structured world of the scientific method. We're going to see how the everyday stuff scattered around our houses can literally become the ultimate learning tools. Okay, here's our roadmap for today. 1. Exploring everyday science. 2. The secrets of spinning. 3. Why do things float? 4. The boat design challenge. And finally, 5. Reflecting on our discoveries. Let's just jump right in.
Kicking things off with Section 1, Exploring Everyday Science.
You know, you really don't need a pristine, sterile lab with white coats and million-dollar machinery to do science. Science actually starts right in our backyards. It's in our kitchens, our playgrounds. Just picture kids making and testing paper boats in a simple puddle of water after a good rain. In the curriculum, we actually follow two characters, Mira and Dhruv, who run outside to do exactly this. Some of their boats float beautifully, while others just flip over immediately and sink. It's a very playful, hands-on aesthetic. But hey, don't let the simplicity fool you. That muddy puddle, it's a laboratory, and those paper boats are their very first real experiments.
To turn all that fun play into actual science, the curriculum introduces this brilliant pedagogical framework. It's a super simple three-step mindset. I observe, I wonder, and I think. First, you notice something happening, like, say, that coin shaking. Then, you ask a question. Why does it start to shake as it slows down? And finally, you propose a hypothesis, your best guess. I really want to challenge you to adopt this exact curious mindset as we go through the rest of this explainer together.
Moving right along to Section 2, The Secrets of Spinning.
So, the curriculum asks students to build their own spinners out of really basic stuff like cardboard and toothpicks. Now, what's super interesting here is the deliberate contrast in the variables. Students are asked to make one spinner with the toothpick dead center in the cardboard, and another with the toothpick poked way off to the side. Let me ask you, what do you think happens? Naturally, the one with the hole right at the center remains perfectly upright and spins like a dream, while the off-center one just completely fails to balance and flops over. It's a direct, totally tactile lesson in the physics of center of mass and balance.
But the variables don't just stop at the physical shape. Imagine you paint a spinner with contrasting primary colors and give it a really rapid spin. What happens then? The colors actually blend together, creating entirely new visual observations and these crazy optical illusions while the object is in motion. We're taking a single variable, changing it, and observing a completely different physical outcome. It's so cool.
The crucial point here is that spinning isn't just some neat toy trick. It's a foundational mechanical concept. And the text brilliantly connects this back to history and culture by introducing the charkha, this traditional spinning wheel famously used by Mahatma Gandhi to make handmade clothes, operates on the exact same principles of rotational motion that the students were just testing out with the cardboard and toothpicks.
And this builds perfectly upon another cultural touchstone, the lattu. These spinning tops have literally been used in India for thousands of years. Originally they were made of clay, though now you usually see them made of wood. By connecting the dots between a handmade cardboard spinner, a massive historical tool like the charkha, and an ancient toy like the lattu, the curriculum shows that the laws of physics are completely universal and timeless.
Which brings us to Section 3, Why do things float?
Okay, let's play a quick guessing game. And look at this data collection. The curriculum sets up this awesome experiment to break a very common misconception. You know the one, heavy things always sink and light things always float. Students have to guess what will happen before dropping an item into water, and then record their actual observation. A leaf is light, so yeah, it floats. An iron nail is heavy, so it sinks. But what about an empty steel bowl? It's heavy, it's made of metal, it's way heavier than the nail, so what's your guess? When students actually place it on the water, they're blown away to discover that this heavy steel bowl actually floats.
And this elegantly leads us right into the core scientific twist of the buoyancy lesson. Take a piece of regular everyday aluminum foil. If you spread it out or shape it like a little cup, it floats. But if you take that exact same piece of foil, meaning the weight hasn't changed one single bit, and press it tightly into a dense little ball, bam, it sinks straight to the bottom. This proves conclusively that shape, and specifically how much water an object displaces, dictates whether it sinks or floats. It's not just about weight.
Now for the really fun part, Section 4, the Boat Design Challenge.
So, the students are tasked with organizing an exhibition in their classroom, and they have to engineer their own boats using locally available materials. Just think about this wildly diverse list for a second. Paper, cardboard, ice cream sticks, clay, and even coconut shells. By providing such a varied list, the curriculum is totally forcing the students to think critically about the properties of different materials. Like, will a coconut shell be naturally buoyant? How in the world do we use clay to waterproof a cardboard hull without making it too heavy to float?
But honestly, the real learning happens after the boats are built. Students have to evaluate their designs by comparing the strengths against the challenges. Maybe your boat is super strong and doesn't break, but it tips over way too easily. By comparing these outcomes with their classmates, it encourages true critical thinking and structural iteration. There are no strictly wrong answers here. There are only designs that can be tweaked and improved upon through continuous problem solving.
Finally, Section 5, Reflecting on Our Discoveries.
The vibrant "Let Us Reflect" prompt from the text signals a really distinct shift in the curriculum. We are moving away from the purely hands-on stuff, like splashing in those puddles and gluing ice cream sticks, and stepping into the realm of deep, scientific inquiry. It's time to synthesize everything we've learned.
And here is one of the exact reflection questions posed to the students. I actually want to pose it directly to you right now. How would you make a floating object sink and a sinking object float? Think back to the aluminium foil. We know we can make a floating sheet of foil sink by crushing it into a tight ball. But what about a sinking object, like a heavy lump of clay? Well, applying our new lessons on shape, if we take that sinking lump of clay and mold it into a wide, hollow boat, it's going to float. We literally just used variables to manipulate physical reality. How amazing is that?
This quote beautifully summarizes the entire goal of this curriculum. It says, "How things work nurtures students' natural curiosity to try out and observe common phenomena. They will discover the patterns and develop a sense of wonder." You see, it's not about memorizing complex equations or boring theoretical jargon. It's about taking something as mundane as a Baber boat or a spinning coin, observing the patterns and keeping that spark of childlike wonder alive as we systematically figure out the universe.
I want to leave you with this final, provocative thought straight from the opening pages of the chapter. Do the things around us always work the same way in all situations? And what changes might be needed to make them work even better? Next time you see a top spinning, a leaf floating down a river, or even a simple coin wobbling on your desk, I really hope you look at it through this new scientific lens. Observe, wonder, and think. Thank you so much for joining me on this explainer. Keep questioning how things work.